Hi everyone, I'm providing you this additional tutorial, video tutorial on causality. In the lecture notes and assignments, we don't have that many questions on causality. So here is one supplement, and hopefully I'll provide you a little bit more on linearity and time invariant or time invariant system. The concept of a causality system is fairly straightforward. It's not any thing like a linearity. You have a precise mathematical proof you wanted to do. And here's just description. So all you need to prove, okay, is to show that the system, output has to be dependent only on values input in the past or in the current. Okay, so then that's a causal system. So t minus t0. So for any instant. However, if you can provide an instant, okay, any instant, that shows that the system output depends on future input, then the system is causal. Okay, so that's the idea. Okay, so here I'm giving you some more exercises here. Okay, so here's all the systems. Okay, you can pause the video and try yourself on all of this data here. Okay, and I will proceed on to try to solve and give you a quick demo of all this system here. Okay, so let's take a look at the first one. Okay, the first one here. Okay, so the first one is y of t equal to 1 plus x of t and cosine t plus 1. In this particular one, as we have to know, first of all, as we don't know, is what's the input, what's the output. Okay, so apparently in this case, input x of t, okay, output y of t. Okay. Now, the other thing is, you look at this one here. What it appears to you is, here's t minus t plus 1. So your first impression is, well, if I let t equal to, let's say, 1, right? And then it appears that y of 1, okay, equal to x of 1 and cosine 2. So you might wonder, well, does that mean that my current input, current output depends on a future time or future input too? Well, so that's a pitfall here. Okay, so you got to be careful. Is you need to be able to distinguish the effect of the input from those of any other. Okay, so the effect input from those of any other functions used in the definition of the system. Okay. So in this particular case, okay, so input is this cosine t plus 1. This is just a function defining the system. Okay, this is not input. Okay, so in this particular case, then you probably will see that, okay, this particular system is a causal system because y of t, or current output, okay, and depends only on what? On the current input. Okay, so as a matter of fact, sometimes we call this memoryless system. Okay, it doesn't remember any past input. Okay, it only depends on the current input. Okay? So that's why it is the causal system. Okay, so let's take a look at the second one, y of t. So So the second and third one are fairly related. This is like one of your assignments question here. Okay. So in this particular one here, so we take it as a greater than 1. Okay, I think that everybody knows that this is a non-causal system. Okay, so if you're not too sure, so let's let a equal to 2. Okay, so then y of t equal to x of 2t, this system. Okay, then let's say at t equal to 2, and you get y of 2 equal to x of 4. So the current input depends on the future output. Sorry, the current output depends on the future input. So this is a non-causal system. Okay. Yeah. We can also try to show this one graphically, basically. Okay. If I show it graphically, let's see. Okay. So let's suppose that this is my x of t, okay, and this is t1, and this is t2. Okay. So your system, right? All it does is basically what? It's a time compression, because a is greater than 1, right? And a time compression in here, it basically compresses your here and to, let's say maybe something like this is not really compression, but here will be t1 over a, and here will be t1 t2 over a, right? So this is your y of t. Yeah, so y of t equals to x of at, right? So essentially now you see your input is in front of the output. So your output always depends on the future input, and that's why this is a non-causal system. Okay. Yeah. And the third one, when a is less than 1. Okay. So let's just suppose that a is less than 1 but greater than 0. Okay, that's a special case here. So in this case here, it's a similar thing. Okay, similar thing. So if a is greater than 0, but let's say a equal to 0.5. Okay, and you can use the same approach as you did before. You know, you let t equal to 2, and then you start checking the system here. And now in this case here, what you need to be careful here is y, right, of 2 equal to x of 0.5 multiplied by 2 x of 1. Then you see, oh, you know, at the current time depends only on the past input. So it looks like the system's causal. Now, however, you got to be careful here is you have to check, okay, all the time. Okay, so let t equal to -2, see what happens. Equal to negative for this y of -2. And x, right, is 0.5 and -2, which is x of -1. So apparently you see -1, the time at -1 is what it compared to that is the future compared to t at -2. So this is a non-causal case, right? Non-causal system. So you can provide a case showing this is non-causal. Okay. As a matter of fact, you can also try to show this graphically. Okay, so let's just say that this is x of t here. Okay, this is x of t. Now, if you do have a y of t equal to x of, for example, at, and a is greater than 0 but less than 1, in their case, let's see, like 0.5 there. So what it does is, right, it's not a time compression, it's a time expansion at here because a is greater than 0 or less than 1. Then if you draw this graphically, and you probably would have a y of t looking like this. So if this is t1 and this is t2, then it'll be t1 over a and t2 over a. right? So that's the case. So this is your y of t. So now you can see that for this side here, right, when t is greater than 0, it appears to be not to be causal because y of t is in front of your input x of t. But over this side, your y of t is actually, right, depends on the future of the input x of t, because this part is in front of this y of t. So that's intuitively and very graphically showing the system is non-causal. Now the fourth one. So this is fairly simple. The integral limit is from negative infinite to t, which is the current time, right? And the integrand is x of tau. So basically, you give at any instant t naught, right? So y of t naught equal to this to t naught, okay? Yeah, and apparently, right, the current output depends on the current input and any past input, right? So any t that is less than t naught, right, will give you the past input, okay? So this is a causal system. So bear in mind that integral, right? Remember in the class we said integral essentially is a summation of all the values, right, underneath this curve x of tau within the limit negative infinite to t. Okay, so let's take a look at this one here. Okay, so this is totally a little bit different here. Okay, so now the integral limit is from 0 to infinite. Okay, 0 to infinite. You might wonder, well, 0 to infinite, does that mean that we are looking at the output depends on the future input? But now you look at the integrand. Okay, the integrand is x of t minus tau. Okay, t minus tau. So if you let t equal to t naught, okay, then your y of t, this is arbitrary instant, okay, any instant, okay, x of t naught minus tau d tau, right, d tau. So tau is a certain number from 0 to infinite, so it's a positive number, right? So t naught minus tau means it's a value less than t naught, right? Less than t naught, and that basically says the integrand here, which is a summation of many instant, okay, but all of the instant, let's see, x of t naught, right, and when tau equal to 0, and maybe at also x of t naught plus 0.5, oh sorry, not plus, minus, it's messed up here, right, and all those things here. But no matter what, these values here compared to the current output, that means they are the past input information compared to the current output, right? And so that means your current output depends only on the current input and past input. So this is a causal signal system. And this actually remind me another thing, don't confuse yourself with causal signal and causal system. Okay, so the sixth one is this. Okay, now this one is different now. Now this one is from negative infinite to positive infinite. Okay, in the question number 4, right, it's only from 0, okay, from negative infinite to t. Okay, so because now it's past the current time t. Now if you let t equal to t naught, right? And you see that, right? T naught is a constant number, but you have infinite, so you will have a many instant that is before, that is after the T naught, right? So which means the current output, okay, will depends on future inputs. So this is a non-causal, okay, system. Okay. So the last one, okay, number 7. So this one here, the integral limits seems to be okay, negative infinite to t. But however, the integrand here, right, inside is x of 5 tau. So this is like your case that we deal with x of at, the case, right? And a is greater than 1. Right? And apparently, you will have many instant, okay? And actually, the y of t, when t is greater than 0, it will depends on, right, the future input. So when tau, right, it is less than 0, it seems okay, right? Seems okay. But when tau is greater than 0, right, and that gives you the idea that the output depends on future input now. Okay, yeah. So this is non-causal system. Okay, yeah. So apparently, when tau is greater than, you probably will have 5 multiplied by 2, right? But when tau is 5 multiplied by negative 2. Okay, so this is past, right, compared to that, but this is the future compared to the instant. Okay, so that's the idea at here, okay, for causal or non-causal. Okay? And many times you need to inspect it. However, there are two things you can you should be careful is, number one, check all the times. Okay? And number two, okay, is the first one here. Okay, don't mix up the input and any other function defining the system. Okay, thank you very much.